Here's the analysis of the data from the molar volume of a gas lab. We've got all the data. We had the mass of magnesium, the volume of hydrogen collected in that big eudiometer tube. The barometric pressure was really just like the atmospheric pressure in the lab room, and that's something now that we just look up on the National Weather Service website. We had the temperature of the water, which is important to mention that we're also assuming that the water and gas are the same temperature. In that big tube, the eudiometer, we had water and gas, and because we couldn't get a thermometer all the way up there to measure the exact temperature of the gas, we assume that because they are in direct contact with each other, they are the same temperature. So here was kind of the setup. We had a little piece of magnesium on the string. When the hydrochloric acid hit the magnesium, bubbles of hydrogen gas flew up the tube and collected in the top portion of the tube. And so those black dots are supposed to represent little bubbles of hydrogen gas. Now the problem, whenever you collect a gas by water displacement, is that you always get what's called a wet gas. In that compartment where we have all the gas up on the top of the eudiometer, we assume that it's all hydrogen gas. But there's always a few water molecules from the surface of the liquid that tend to evaporate. And so they call it wet gas because it's a mixture of mostly hydrogen, but a little bit of water vapor. And so in question 1, we want just the pressure of the hydrogen gas alone in the eudiometer. But the barometric pressure is sometimes referred to as like the total pressure acting upon the system. That's actually a combination of the pressure from both gases in that upper part of the eudiometer. So we do something in number 1 that's pretty typical in reference to Dalton's law of partial pressure. And so Dalton's law is for a mixture of gases, and it just says that the total pressure is a sum of the pressure from each individual gas plus the pressure of the water. It's kind of a funky plus sign, but it's fine. And so we've got 2 gases in that upper compartment. I want just the pressure of the hydrogen. That's the gas I'm studying. The barometric pressure is always known as the total. And if this were like a free response question, they would just tell you the total pressure or the atmospheric or barometric pressure. 746.76 millimeters of mercury. But then in order to figure out the pressure of the hydrogen alone, I need to know the water vapor pressure, and then I can just subtract. Well, water vapor pressure is kind of another constant. That's probably something that they would give you if this were part of a free response kind of question. Where here's a chart or a table that's got typical water vapor pressures at various temperatures. And so here I could just look up the temperature of my water and find its corresponding water vapor pressure. Here I kind of estimated a little bit because our water temperature was in between 22 degrees and 23 degrees. So kind of proportionally in there, I'm going to go with 20.7 millimeters of mercury as the water vapor pressure at 22.7 degrees. But again, this is probably something that would be given to you along with the total pressure. These are kind of considered constants. So I've got the hydrogen, that's what I'm looking for, and then I'm going to take that 20.7 millimeters of mercury. They would probably give me this guy and this guy. And then I'm solving for the hydrogen. So now it's easy, right? All I have to do is subtract. And so when I subtract, I'm looking at about 726.06 millimeters of mercury. And that would be the pressure of the hydrogen gas alone. You'll probably always need to do a calculation like this if you're dealing with lab data that involves collecting a gas by water displacement, where there's just going to be some water vapor mixed in with the gas you're intending to collect. And we want just the pressure of the hydrogen alone. It's an easy little calculation, just subtract off the water vapor pressure. Fantastic. Okay, so number 2, we're going to do a little stoichiometry. Eventually, we'll balance equations and look at different types of reactions, but you might recognize this reaction. You probably would have either done this reaction last year or maybe balanced the equation. It's one of those single replacements where a single element is replacing an element that's in a compound. And so the single magnesium will replace the hydrogen. I'll form bubbles of hydrogen gas, and then the magnesium will bond with the chlorine, and it'll just be an aqueous solution. That's the solution that came out the hole at the bottom of the stopper. Alrighty, so we're going to do stoichiometry. We have the mass of magnesium, 0.061 grams of magnesium. And we used a small amount of magnesium and approximately 10 milliliters of hydrochloric acid. Well, that 10 milliliters of hydrochloric acid was probably more than what we really needed, so that the magnesium was purposely the limiting reactant. When the reaction stopped, the piece of magnesium metal was totally gone. It was completely consumed. Now, the liquid that was left in the tube was mostly water, but I'm sure there's a little bit of excess hydrochloric acid in there as well. But as long as I know that the magnesium was gone, it was the limiting reactant, I can do a little stoichiometry to figure out, well, if 0.061 grams of magnesium reacted, well, before I can compare that to the hydrogen, I need to get it out of grams and into moles. Oh, this feels really good. We haven't done a mole calculation in a while. On my periodic table, 24.30 is the molar mass of magnesium. And so grams and grams would cancel. And now if I plug this in my calculator, technically I'm at moles of magnesium, which I could stop right there because I see that in the balanced equation it's a 1-to-1 ratio between the magnesium and the hydrogen. But if you just want to get it set up, then technically I'm canceling moles of magnesium and I'm switching it to what I want, moles of hydrogen. Now obviously it could be a reaction where it's not a 1-to-1 ratio. This one is, and so it's pretty easy. I'm going to plug this all in my calculator now. And now technically my first number only has 2 sig figs, the 6 and the 1. But I don't know, I just don't want to lose too much precision because these are going to be really tiny numbers. Like I'm only looking at 0.0025. I'm going to leave a 1. I'm going to leave 3. I just don't want to lose too much precision. And that would be moles of hydrogen. So looking at the stoichiometry, I'm consuming all of the magnesium. I should produce about 0.00251 moles of hydrogen gas. Fantastic. Alrighty. Then, number 3, we're going to use the ideal gas law to calculate the theoretical volume of hydrogen that should have been collected at lab conditions. So the theoretical basically means like under the given conditions in the lab, 0.00251 moles of hydrogen should occupy what volume? The ideal gas law is pertinent. PV equals nRT. This is a great gas law. It's in the packet and it's just plug and chug. P is the pressure. So this is all going to be in reference to the hydrogen gas in the lab. It's going to be the answer from question number 1. That should have been the corrected pressure of the hydrogen gas. 6 millimeters of mercury. That was really my answer from number 1. Once I got rid of the pressure from the water vapor, there's the pressure of the hydrogen. V, volume, is going to be my variable. N stands for number of moles, 0.00251. And then comes R. R is your gas constant, and it's in the AP equation packet. There's a section on gases, liquids, and solutions, and you'll find all of this information, as well as other equations. So sometimes people get a little tripped up on choosing the right version of R, the gas constant. I'm going to tell you this right now, that for gas laws, we will not be using this guy. Which you're like, but it says it's a gas constant. Not this one yet. I mean, eventually we'll use him, but not with Pervner. We'll use him with a different equation. So don't use the one with joules. We're going to use that when we get to some thermochemistry, thermodynamics, but not joules now. Instead, you're looking at the other two options for R, 0.08206 or the 62.36. Those are for Pervner because the units of the constant match the units of the variables in this equation. There's pressure and volume and temperature and moles. Now, to choose the right version of R, you're really just looking at the pressure unit. Everything else is the same. So if your pressures are given in atmosphere, you're going to use the 0.08206. If your pressure is in torr, you're going to use the 62.36. Well, we've been kind of working in millimeters mercury, but it's okay because they will also tell you this, that millimeters of mercury and torr are equivalent to each other. So I'm going to use the 62.36. Alrighty, so I'll use 62.36 as my constant. And then the other thing we just have to be aware of is that when I use this constant, all of the units of the constant need to match the units in my work. So like my pressure is now in either torr or millimeters mercury. My volume is going to come out in liters. N was my moles, I had that right. But then T, my temperature, needs to be in Kelvin. For any gas calculation, your temperature must be in Kelvin. And so now I need to go back and find my 22.7 degrees Celsius. And in the packet, they'll tell you in this section, they'll give you the conversion between Celsius and Kelvin. So if I add 273, I'm at 295.7 Kelvin. Then I can just plug this all in, and out comes my volume. And again, I think I'm going to maybe leave 3 sig figs on my volume. So maybe like 0.0637, and it's going to come out in liters. That's why it's kind of a small number. It's in liters. And so we can calculate the percent hydrogen collected as a percent yield in a sense. Percent yield is actual over theoretical times 100. So actual comes from your lab data. This is the actual volume that we collected. Whoopsies. 67.20. Now that was in milliliters. The theoretical is what I just calculated. Now it was calculated in liters, and so when you do this percent yield, as long as you're using the same unit, it really doesn't matter which. So I could just take that as like 63.7 milliliters. Hey, this isn't too bad. I mean, gas labs are really tricky because a gas can escape from almost anywhere. And so if I didn't have like a perfect seal, a gas could escape. And there's also an error in this particular lab that might cause me to create a little extra gas. It might seem that I created a little extra gas. And so we're going to be a little over 100% yield. And I don't know, maybe I'll say about like 105, 106, somewhere in there. There we go, 105.5. A little bit over 100. But gas labs are tricky. There's Just lots of room for error. So I'm okay with that. Like, we're pretty close to 100% yield. All right, number 5. Number 5 is having us use this combined gas law. And I'll tell you right now that it's not in the packet. So you're probably not going to have to do this in a typical AP free response. But for the lab, eventually I'll kind of show you what we're trying to do here. So the combined gas law looks like this. And maybe you used this in first year chem. P2V2 over T2. It's a combination of Boyle's law, Charles' law, and Gay-Lussac's law. It's got the pressure-volume relationship, the pressure-temperature, the volume-temperature relationship. They're all in there. And so here's what we want to do. We're going to use this combined gas law to calculate the volume of hydrogen collected if the lab room would have been standard temperature and pressure, which it was not. And so we're going to take, let's say, the P1, V1, and T1. And we're going to set this equal to lab conditions. And then P2, V2, T2. These are going to be conditions if we were at standard temperature and pressure. And so it's going to be just a lot of plug and chug. In the lab, the pressure of the hydrogen was the answer from number 1. The 726.06, and that was millimeters of mercury. In the lab, I collected 67.20 milliliters of gas. And in the lab, the temperature was 295.7 Kelvin. For any gas calculation, we need temperature in Kelvin. And that just comes from experimentation that, for example, like pressure and temperature, volume and temperature, they should be directly proportional. That if I double the temperature, I double the volume, or I double the pressure if it's a rigid container. But that only holds true in the lab if you double the Kelvin temperature. If I double the Celsius temperature, if I go from like 20 degrees Celsius to 40 degrees Celsius, I mean, the volume would increase or the pressure would increase, but it will not double unless you double the Kelvin temperature. Okay, so I already had it in Kelvin from number 3, so I plug her back in. Now we're going to use the conditions at standard temperature and pressure, STP, which they tell you in the packet. So for example, they're going to tell me that standard pressure is 1 atmosphere. But they also tell me that 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. So I just have to make sure that my units jive. 760, I'm using millimeters of mercury. The volume is what we're going to solve for. I want to know what would be the volume if this gas were collected at standard pressure and standard temperature, which they tell you is 273 Kelvin. And so, I mean, we were not obviously at standard temperature and pressure in the lab, and in fact, we're usually not. Standard temperature would be 0 degrees Celsius. And so, yeah, our lab temperature was a little higher, and our lab pressure was a little lower. Now, without plugging this in, both of those would make me think then that the new volume, if this reaction were run at standard temperature and pressure, I'm thinking the volume would be a little bit less, right? Because standard pressure is a little bit higher, so higher pressure would make the volume smaller, and the temperature is a little lower, and that would also make my volume a little smaller. So we do a lot of algebra, and we plug this all in our calculator, and oh brother, I'm going to say that the new volume is about 59.2 milliliters. There we go. Now, with this little equation, the volume doesn't have to be in liters because I'm not using like a gas constant, but my temperature has to be in Kelvin. As long as my volume unit is the same, milliliters will be fine. So just what I expected. At standard temperature and pressure, the volume would be a little bit lower. Okay, why do I care what the volume would be at standard temperature and pressure? That's for number 6. Using the volume of hydrogen gas produced at STP, which is what we just calculated, now we want to determine the molar volume of hydrogen at standard temperature and pressure. Molar volume is the volume of a mole, or liters per mole. We're going to go in liters per mole. I'll kind of show you why. So if I go liters, my answer in the last calculation, I plugged it in as milliliters. No biggie. I'm just going to now flip the decimal spot 3 places, and we'll just say 0.05927 liters. So that was just my answer from number 5. I corrected for the new volume if lab conditions would have been standard temperature and pressure. All right, so there's the volume that would have been produced. And then moles is just how many moles of gas were produced. So I can go all the way back to like, what, number 2 maybe? 0.00251 moles. So there's the volume at standard temperature and pressure. The moles would be the same. It doesn't matter what temperature or pressure. The number of gas particles would be consistent. So now we plug these in and we divide, and yay! 6. And the unit would be like liters per mole. That's the volume of 1 mole. 1 mole of hydrogen, with our lab data, would have occupied a volume of 23.6 liters. Well, here's what we were getting at with this whole STP thing. That when you look in the packet, this is a constant. 1 mole of any gas, behaving ideally, at standard temperature and pressure should occupy a volume of 22.4 liters. This is kind of a constant. You could use this in stoichiometry. You could use this to find like the number of moles of gas or the volume of gas. If you knew that you had 2 moles of hydrogen at standard temperature and pressure, then the volume should be 44.8 liters. Or if I had 44.8 liters and they wanted to know the mass of the sample, well, then I could say, oh, well, that would be 2 moles, and then I can change moles to grams. As long as you're at STP, this is a constant, 22.4. And so that's why they had us convert our volume to the volume if we would have been at standard temperature and pressure, so that we can compare this to the 22.4. Which I don't care so much about calculating a percent error. I don't need a percent error. But we could just put down here that the theoretical would have been 22.4 liters per mole at STP. That's the volume of 1 mole of any gas, because the volume would just depend on the number of particles if we were at like the same temperature and pressure. Okay, so again, we're a little bit high, but so was my percent yield. So like it seemed as though I had a little too much gas, which is kind of why I don't need to calculate a percent yield and a percent error. I mean, right here, like this was a little high because this was probably a little bit high, maybe. Which then I used that volume down here. So if that was a little high, my new volume at STP was probably a little bit too high. So eventually here, 8 and 9 are going to look at two really common sources of error. And then we'll try to see which maybe would apply to our data. In the lab, a student noticed that an air bubble had leaked into the udiometer as it was inverted into the water bath. What effect would this have on the measured volume of hydrogen gas? Okay, well, think about this. So here was my tube of gas. And I thought it was all hydrogen, and I get it. There's a teeny tiny little bit of water vapor in there. But what if I maybe didn't put the stopper on real tight? Or maybe, there's a hole in the bottom of there's like a hole in here. And that's so that the liquid can escape the tube as the gas is being produced. What if I didn't have my finger on it and some of the water kind of dripped out and I got an air bubble up here? So what if up in here there was an air pocket? And so I thought that I had collected, I thought that this here was about 67 milliliters of gas. I thought it was all hydrogen, maybe just a teeny tiny little bit was water vapor. But do you kind of see the error then? I thought that was all 67 milliliters of hydrogen, but what if this up here was a little air pocket for, I don't know, 3 milliliters? This is air. What if there was a 3 milliliter air bubble up on top? Well, really then I may have only collected 64 milliliters of hydrogen. And I didn't think about that little air bubble up on top. Oh, source of error. So what effect would this have on the measured volume of hydrogen gas? In this case, maybe I measured 67, but it was only supposed to be 64. The measured volume is going to be too high. It's higher than I expect. Would the calculated molar volume of hydrogen be too high or too low as a result of this error? Well, look at where we carried that number through the calculations. So right away, that 67, maybe that's too high. That's supposed to be 64. Well, then I used it in PervNert, and I got, that was, I should say, the theoretical. I used it in number 4. This would have been too high, which then I used down here, that's too high. This is maybe too high, and then I used that in the numerator over here. That volume is still too high. So again, I would expect then that the molar volume is too large. That's supposed to be the liters of hydrogen per mole, but I thought I had more hydrogen than what I maybe really produced. So we're just going to write a little sentence or two explaining how that error would affect my data. Okay, so one common error would have been a little leak. It could have been from the stopper, or maybe I didn't fill it all the way with water. And even before I put the stopper in, maybe there was a little air pocket. Here's another common error that we tried to remedy. A student noticed that the magnesium ribbon appeared to be oxidized. And so the metal surface was kind of black and dull rather than silver and shiny. What effect would this have on the measured volume of hydrogen gas? Okay, so I measured, let's see here, where was my mass? I measured 0.061 grams. And I thought that that was all magnesium. Well, we tried to clean the magnesium well, because you do get this magnesium oxide coating. The magnesium is pretty reactive in air. And so what if I didn't clean it well enough? Well, then that 0.061 grams, that's not all magnesium. That might be magnesium plus a little magnesium oxide, or in other words, oxygen. There might be a little bit of oxygen in that mass. Oh man. So that mass is too high, that's not all magnesium. And the oxygen is not going to react with the HCl and produce hydrogen gas. All right, well, how is that going to affect the measured volume of hydrogen gas produced? Well, I thought that this was all magnesium, that it would all react and produce, an equal molar amount of hydrogen. But if some of that's not really magnesium and it's not going to react, the measured volume of hydrogen is going to be lower than I expect. What if I say less than expected? I mean, I thought that I had 0.061 grams of magnesium, but really I had less. I didn't have that much magnesium. And so the amount of hydrogen I produce then is going to be maybe less than what I expect. Like when we did this calculation now with PervNert, actually even if I back it up to number 2, I did this calculation assuming that the entire mass of the sample was magnesium and then that it should produce 0.00251 moles of hydrogen. Well, really some of that mass is not magnesium, so there's going to be less than 0.0025 moles of magnesium and less than 0.0025 moles of hydrogen, which then would have affected number 3. And what I would expect in the lab now is less than what I just calculated. Oh, now when I think about it, yeah, dang, that's not all magnesium if I didn't clean the piece of metal well. How would this affect your molar volume of hydrogen? Well, you could think of it from one of 2 ways. That, well, now my volume of hydrogen is going to be less. And so if the volume in the numerator is smaller, then that would make my molar volume smaller. Or that my moles, that mole number, that's going to be off too, right? Oh yeah, like that moles, that's too large. I really didn't have 0.00251 moles of magnesium or moles of hydrogen. So the volume in the numerator is going to be too large. The moles in the denominator, or I should say the volume is too small. The moles are going to be too large. Either would then make my molar volume less than what I expect. And so with our data being a little bit too high, we had a little over 100% yield, which is obviously impossible. It's probably more likely that we had maybe a little air bubble in there. And so that's where I would go with my conclusion. When I write the conclusion, I'm just going to kind of briefly describe the purpose of the lab. And we were trying to confirm this. We were trying to confirm the molar volume of a gas. The volume of 1 mole of any gas at STP. It should have been 22.4, and we're in the ballpark. It's still really good data. Ours was just a little bit high. So we're going to explain the percent hydrogen collected. Why would it seem as though we collected extra hydrogen? But don't worry about the percent error. One of those is plenty. I mean, they lead to the same conclusion. The other thing that's good to write about in a conclusion is ways to improve the results. Obviously, running multiple trials is always a good thing. Multiple trials might confirm our data. But maybe in this case, maybe I should have put the stopper in a little bit tighter. Maybe I should have made sure that the hole in the bottom was covered when I inverted the tube. I should make sure that the tube was totally filled with water so that there wasn't an air pocket to begin with. Those might all be things that I would just make sure I do well if I could repeat the procedure. So all you have to do then is jot down your answers and your calculations, show all your work, write your answers in complete sentences. My conclusion is just a short paragraph. You can write that all on paper and then upload photos of your work to this document and then submit.